Now, we've already discussed similar polygons, but today we're going to emphasize a similar triangle. So for today's agenda, I'm going to discuss the difference between similarity and congruence. After that, we're going to have some similarity tests to learn, and I'll show you some examples on how to apply those tests. So let's begin with the difference between congruent and similar. Now, hopefully in the previous class, you saw congruent figures. So for congruent figures, all corresponding sides are the same length and all corresponding angles have the same measure. So basically they have the same degrees. Now suppose you had this triangle here, triangle A, and let's say that you copy it. And now we have another triangle that's exactly the same, but this one's called triangle B. There are two different triangles, but what's special about these triangles is that they have the same measurements for angles. So here all of these angles should be the same, and then all of the lengths are the same as well. So if this is 2, this is 3, and then this is 4, this one also has to be 2, 3, and 4. When we have exact copies of another thing, we say that those things are congruent. So here triangle A is congruent to triangle B. You can think about congruent figures as identical copies. Similarity is a bit different. For similar figures, all corresponding angles have the same measure and all corresponding side lengths are proportional. So here, let me show you an example. So suppose we have a triangle here, and let's say we want to make a copy of this. However, this copy is going to be a little bit different. The difference is that here, this copy is going to be scaled. You can either make it bigger, which would be an enlargement, or you can make it smaller, which would be a reduction. And here we can say that the original copy was called A, and then the dilated figure is A prime. This being the pre-image, and this being the image you get after that scaling factor. So similarity, you can think about it as a smaller or bigger version of the original copy. And taking this into account, here's what this means. So here, like congruent figures, the corresponding angles are the same. So here, let's say all of these angles are the same. However, the lengths intuitively should not be the same, because again, we're making the picture either smaller or bigger. So suppose that this was 2, this was 4, and then this was 6, and let's say this one was 8, 16, and 24. We can clearly see without doing too much work that the angles are congruent, right? Corresponding angles are congruent. And then to see that the side lengths are proportional, we get corresponding lengths and begin creating ratios. So 2 over 2 corresponds to 8, and here we get 1/4 as the scaling factor. Let's get the other side, 6 over 24. You're gonna get the same thing, 1/4. And then for the last part, 4 corresponds to 16. So 4 over 16, this also gives us 1/4. And here, you can use the decimals here if you'd like. So here, this is 0.25, 0.25, 0.25. So that's what this definition means. The corresponding angles are congruent and corresponding sides are proportional. That's similarity. For congruence, everything is the same. So again, think about identical copies for congruent and smaller or bigger versions of the original copy for similarity. And this is what we're going to be focusing on. So let's check out some tests. Let's begin with the angle-angle similarity postulate. Now, something that you might have learned in middle school was a bunch of postulates with determining if two triangles were congruent, such as side, 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 side angle, side, etc., etc. It turns out that for similar figures, we have similar postulates, beginning with the angle-angle similarity one. And here we have that symbol for similarity. And here's what this says. If two angles of a triangle are congruent to two angles of another triangle, then the two triangles are similar. With these problems, what I usually like doing is I like to have my triangles facing the same direction. So I'm going to grab the smaller one and rotate it so that it is facing the same direction as that bigger triangle. By doing this, it's easier to see which angles correspond and which sides correspond. So here A corresponds to W, B corresponds to X, C corresponds to Y. So let's check out the angles. These 3 tick marks on Y and then these 3 tick marks on C identify, or they tell the reader that they have the same measurement. The same thing for B and X. So on this example, we have that angle X, here I'll use angle X is congruent to angle B, plus we have angle C congruent to angle Y. We meet the criteria for this postulate, so we can say, or we can claim, that triangle, now we have to choose a direction, so I'm going to choose A, B, C. So here triangle ABC is similar to triangle, and now we have to mimic this pattern with the other figure. So we went down and to the right, so here we're going to go down and to the right, WXY. And that's the angle-angle similarity postulate. Let's check out the next one. Now we have side-side-side similarity. This is what it says. If the corresponding sides of two triangles are proportional, then the two triangles are similar. Let's take a look at these figures and notice that these two triangles are already facing in the same direction, so we don't need to rotate either of them. We can say here that AB corresponds to A, and actually let me change the letters of these angles. Now we can say that AB corresponds to WX, BC corresponds to XY, and CA corresponds to YW. Let's begin to take ratios and hope to get the same scale factor. So let's get AB and divide it by WX. So here we get 50 over 5. And 50 over 5, that's going to be 10. Now let's get the next side. So we have BC corresponding to XY. So let's get BC divided by XY. BC is equal to 40, XY is equal to 4, and 40 over 4, that is 10. So far we're looking good. We just have to make sure that the last pair of corresponding lengths are proportional to 10. So here we have AC, and that corresponds to WY. So let's get AC and divide it by WY. AC is 30, WY is 3, 30 over 3 is 10. Check, check, check. And that verifies this criteria that the corresponding sides are proportional. Since they're proportional, we can claim that these two triangles are similar. So we can claim that triangle, let's begin with the big one, and I'm going to choose my direction, so I'm going to begin with A. So triangle ABC, and then I'm going to have to mimic that pattern. So triangle ABC is similar to triangle WXY, and that would be that would be by the side similarity postulate. Let's go ahead and check out the last one. So for the last one, we have side angle side similarity theorem. And what this says is that if one angle from a triangle is congruent to one angle from another triangle, and the two sides of each triangle that include the angle are proportional, then the two triangles are similar. I've included some lengths, and now something I need to point out is that even if it's not specified, vertical angles are always going to be congruent. So let's go ahead and verify SAS here. And I'm going to get this triangle CED. So triangle CED, and I'm going to rotate it so that it's facing in the same direction as triangle ABC. So I rotated triangle CED. So here, let me emphasize this part. So this triangle became that yellow one. So now let's see the angle and the sides. And clearly here we can see that angle C is congruent to angle C. So it's congruent to itself because these two triangles share the same angle. So here we can say angle C is congruent to angle C. Now I have to verify that the corresponding sides are proportional. So I'm going to get AC and divide it by DC. So I have AC over DC. AC is equal to 9 and DC is equal to 3. And 9 over 3 is the same thing as 3. Let's check out the other side. We have BC and we gotta divide it by EC. So I get BC over DC. BC is 6. DC is, sorry, it should be EC. Here, EC. That's equal to 2 and 6 over 2 is 3. And here we have that the two sides are proportional and the angle in between those two lengths, those angles are congruent. So here we can claim that triangle CED. So I started here, went left and went up. So I have to start here, go left and go up. Triangle CED is congruent to triangle CBA. And that's by SAS. And I meant similar, not congruent. So triangle CED is similar to triangle CBA.